I will talk about capable exascale and beyond Moore's law. So if you followed high-performance computing, you know that about since 2006, 2007, there has been a discussion about how we get to exascale. It's already 7, 8 years later, and we still are not even halfway there. I will comment about this. This is a big goal, and I will also say a bit about beyond Moore's law, and we'll get to that as we speak. So I want to start out with this iconic picture. And you see John von Neumann and Robert Oppenheimer in this picture, Princeton, 1952. And I think that picture, and this is, I think, a very good introduction for the whole talk, gives you a sense on why we're here today, all of you, whether you're a supercomputing expert, whether you make apps for a phone, whether you use just occasionally some computing technology. Because the origins of all the computing that we're doing today are in this picture. And in this picture, you have a person who is intimately connected, of course, with the creation of nuclear weapons and the atomic bomb. And you have another physicist in there, John von Neumann, who is really intimately connected with computers as we see them today. And this is actually, and it's often forgotten because we try to, in a sense, neglect or even deny the origins and the history of computing. The roots of computing as we do today are in computational physics and are in the Second World War, both in terms of cryptanalysis, and the work that Turing did in England was driven by cryptanalysis. The work that was done in the Manhattan Project was driven by building nuclear weapons. So the very first codes that were developed and the first software that was written for computers, and why we invented digital computers and the Neumann architecture to begin with, was that we wanted to build systems that could solve computational physics problems. Computational physics problems for the experts are today 3-dimensional problems done on grids or on unstructured grids or with finite elements, and they focus on floating point performance. So it is truly remarkable, and this is what my next slide shows, and this is an important thought, is that we went from the bomb to the cloud. And what I mean by going from the bomb to the cloud is that the computers that we use today were built for the left, and we're using them today for the right, which means that we still have the very same architecture, the von Neumann architecture with floating point calculations, with a stored program that were originally developed for computational physics application to do everything we're doing today. Everything you're doing today. That is, if you listen to music, if you take photos, if you do big data, if you do web searches, if you do social networking, if you store something in the cloud, if you just do PowerPoints, everything we're doing today is done with an architecture which has those origins and was actually fairly optimal for those origins. And that's something that is actually truly remarkable because this has been more than 60 years ago. So then you could say, well, why is that? And the reason why that is actually something that we all still live off and know very well about, and this is Moore's law. Because the underlying technology, since the late 60s, basically CMOS-based or semiconductor-based technology, the integrated circuits, have, because of Moore's law, doubled. We had exponential growth for this incredible long period of time. Actually, if you go back and look at some things that Kurzweil put into his books, we had actually performance doubling even before the current circuit-based computers, when we had vacuum tube computers, even before when we had mechanical computers. So computing has been on this incredible growth curve, but what's important is that we had 2 technology transitions since the 1940s, and yet we continue to have this exponential growth, and since the late 60s we of course have the integrated circuit exponential growth based on Moore's law. Now, because computers were getting faster and faster by such an incredible rate, we never had to spend any brain power at all rethinking architecture. We just left the architecture alone. Basically, why bother changing the architecture? Why changing the infrastructure? Why changing any software that has been written for the last 20 or 30 years? Because as sure as whatever, it's not raining in February in San Francisco, the performance of the processors was coming faster and faster. So that's why we can do all the things that we're doing today with the same old architecture, because we got this incredible growth thanks to Moore's law. So if you believe what I said now, then here's a corollary, and this is, if we hit the end of Moore's law, then the only way to continue performance growth in computing and come to new things, we have to reinvestigate and have to go back and find out what can we do and how do we do new architectures. So I believe that, and I will give you some arguments later which are based on the top 500, that we're in a phase that, at least for integrated circuit type computers, CMOS-based technology, we're hitting a point where we're slowing down and maybe having the end of Moore's law. So therefore, this is my first argument. So my first argument is we'll look at where we are today and make an argument that we're ending Moore's law, that we're coming to the close of to the end of Moore's law, at least the Moore's law that Gordon Moore formulated in the late 60s. And then there's a two-dimensional space. One space direction that a lot of you who are in electrical engineering and applied physics have pursued is to look beyond CMOS and say, what can we do with other fancier technologies to accelerate computing? But in recent times, there was a question of, can we also change the architecture and do things in a non-von Neumann space? And if we do beyond CMOS in the non-von Neumann space, where there's a lot of excitement in quantum computing, and very recently there's also a lot of excitement in neuromorphic computing, brain-like computing, which is a non-von Neumann architecture, but built in traditional technology that is in CMOS technology. So I will look at this two-dimensional space, look at where we are today, beyond CMOS, then quantum computing, and then neuromorphic computing. And I would say in many of these things, I give you opinions. So I'll give you some facts, but the conclusions are mine. So be free to challenge me and ask me questions on this. So there is an observed slowdown of HPC. Miha was talking about the top 500 list. I will talk about this a little bit more, how you see that there is a slowdown in HPC. I believe that we can do some technology changes and we will get to usable exascale. So I would give the traditional high-performance computing, as it is now foreseeable for the next 10 years, enough growth that we will get to something like a usable, that is an exascale machine where we actually get exascale application performance in the early 2020s. I will make a strong argument why I don't believe in quantum computing. I think that quantum computing is not going to be the answer that will replace traditional high-performance computing, not now and not in 2025. You can debate this at length, and I'm happy to debate it. And then I will talk a little bit about how to envision a non-von Neumann world. And again, since Miha in the introduction said, where are the opportunities? I think the opportunities are in the non-von world. So those of you who have been to supercomputing recently will find that today HPC is a very, very thriving business. Business for the companies that are involved in, more or less. Very, very strong intellectual activity. If you look around at supercomputing, there are 13,000, 14,000 people coming together every year. There are hundreds of vendors that sell machines and any type of other things, services, components. The field really is thriving. Supercomputing is worldwide of interest. You will see there the Chinese are pushing this very hard. The European Union has created a praise collaboration of all the countries. It has become a very critical technology all around the world. Russia entered supercomputing. There are supercomputers in India. It's everywhere. Because, as you probably know, it has impacts not just in science, but in national security and also in economic competitiveness. So from this point of view, we're doing really well. And here's my first top 500 slide. So most of you raised the hand and you know about top 500. This is, in a sense, an indication that the top 500 is an indication that supercomputers are doing really well. Here you see the since 1993 performance development of this measurement, the LINPACK performance of the 500 most powerful supercomputers in the world. You see the sum is the blue line. The number 1 system is the red line, and the green line is the number 500 system. And so the truly remarkable thing is that you see exponential growth on the semi-log scale from the early 90s over more than 20 years now, over more than 40 lists. Yes?
I have a question. Where would you make a difference between supercomputing and warehouse computing?
I think the supercomputers that you see on this list all have, to a large extent, a very strong interconnection network, up to maybe a custom-built interconnection network, like, for example, Cray with areas. And so they not only perform high floating point calculations, but they also have a, relatively speaking, high bandwidth. In a warehouse computer, you have independent clusters that, I'd say, if a system can run Hadoop really well or some similar technology, then you still could run supercomputing-like applications, but you wouldn't get the performance.
So Amazon Web Services or Rackspace
are not on that list. They're not on the list, but we would list them if they would actually submit a LINPACK number. But I think there's a first challenge. It is not as easy as you think to run a LINPACK on, say, an Amazon web server.
And they'd have to run on the full machine.
Pardon?
They'd have to run on their full machine.
And they would have to run the full machine. So it's a challenge. Miha said, I'm not coming necessarily to these events. A while ago, I was at University of San Francisco where they had a flash mob. And they said, everybody bring a PC. And some of the companies provided interconnects. And they wanted to build a computer on the fly and run LINPACK. And they were only able to get about 250 laptops and PCs together. And then the system didn't scale up anymore. So it's not that easy. But I think the big systems are also not on the list because, very simply put, the big commercial companies don't want to be known what systems they have and how large their systems and their capabilities are.
That was since the beginning of top 500. Many of the manufacturers didn't
Yes,
want to.
exactly. Many of the manufacturers didn't want to. And it was, well, I can tell you anecdotes about the top 500. Actually, the reason that I got deeply involved in top 500 was in 1994. In the second or third list, suddenly SGI decided to use the list and put a lot of systems in the list. And then Hans Moyer called me and said, well, you sit right in the middle of Silicon Valley, figure out if all these SGI machines are real. And then I did some tests, and I was convinced they're real. And then later on, I was so surprised how well SGI did that I started working for SGI for a while. So, but this was the first time SGI used the list in 1994 and made a big deal about how many systems they had placed and that they had more systems than Cray. And then all the other vendors were pulled into and trying to use that also as a competitive tool. So now a few vendors decide not to submit. Some systems like classified systems are not always on the list. But in general, it is not, I should make this point here, it is not important. I mean, of course, if you're the owner of a machine, you would like to see the machine, or you don't like to see the machine. And that's not really that important. The important thing is statistically, if you have 500 systems, you get a good analysis of the trend. That's a large enough sample of the high-end market that you can make statements like the ones that I want to make here. So here is the very naive and simplistic thing that a lot of people do. And they say, well, we just take these lines that were good for 20 years, and we extrapolate them forward with a straight line. And it's pretty obvious that with that, we will get an exaflop system by about 2020. And so case closed, things are over, done with it. Now, even if you don't know anything about high-performance computing at all, you should sort of be very much concerned about it, because what you're doing here is doing an extrapolation on a semi-log scale. And whenever you do an exploration of exponentially growing data, very small perturbations in the beginning can give you a big variation at the end. And actually, I will show you this in the next couple of slides, that this is exactly the case here. So if you look very careful, you actually see now that by about 2010 on, those curves seem to be flattening out, which is something I want a couple more comments briefly. So one of the interesting things is that the way you can look at these curves that are flattening out is if you look at the 500 curve and do a straight line extrapolation based on data up to about 2008 or so, you get one extrapolation. But if you take the data since 2008, you get another extrapolation. And so you can actually look at this and see that in June 2008, something happened that changed the slope of this extrapolation. If you go any further, then you can say, well, if you do the same analysis with and I flip through this very quickly, with the total sum, you see that in June 2013, there was a similar breakpoint. And so if you then do on all this the extrapolation out, especially on the sum, you see that the slope is very, very different from where it was historically. So I believe fundamentally that we've seen in the last 5 years a beginning of a turning point, that the growths that you would expect from Moore's law and from parallelism are no longer there. Now, in all fairness, you have to be aware of this, that these curves are actually the product, since we're in exponential space, the product of two factors. The machines have become more and more parallel, and the process have become faster and faster, and both factors equally contribute to the growth. So we may have hit a double problem in terms of parallelism and in terms of the Moore's law growth of the processes. But obviously, there is a problem. Now the question is, Of course, some people say this is just a temporary slowdown, so we can say, why is that? Some people say, well, this is just the long-term effect still of the 2008 recession, because it took until 2000, we had stimulus funding. A lot of the systems in the US are built with federal government. We only see now the long-term effects of lack of investment in 2010, 2011. A lot of people say, oh, it's waiting between technologies. So Intel put out their many-core Xeon Phi marketing called processor, and we still have to see how they will find market acceptance. And a lot of purchases have been holding back and want to see where is Intel really going. There has been, of course, a narrowing of the field. If you can actually say that IBM has reduced their engagement by ending the Blue Gene line. There's no more Blue Gene out there. But there are other things. There's power consumption. The systems require more and more power, becoming more and more expensive to run. And I say, well, this may be an indicator of the end of Moore's law. So you can have a long debate on why is HPC actually slowing down. And as I said, not everybody actually says HPC is slowing down, but I think it is. Two other things is that, as I said, the extrapolation is, of course, a factor of 10 now less if you just take the last couple of years for 2020 than it was 5 years ago. For the last 2 or 3 years, the top 10 machines have been virtually unchanged. Only the number 10 system changed twice. And there is the Coral announcement for 2017, so you probably followed this at supercomputing. So a lot of people say, oh, it's really exciting. We're finally on the track to exaflop. The actual fact is, if you go back to look at announcements, this announcement is about 3 or 4 years too late. We should have had the systems that are now announced for 2017 by 2014 or 2015. That is now. These are 100 to 250 petaflop system. If you wanted to get originally to exaflop by 2020, you would have to have a 100 to 250 petaflop machine by about now. So clearly, there is a slowdown. Things are not going fast. Yes? Miha.
The ease of use and accessibility
Okay.
of the computer.
It's the same. It always has been a difficult, expert-only technology, and it continues to be.
So is any work done in this direction?
Oh yeah, there is a lot of work done. And if you look at, say, the plans that are listed there for Exascale, I'm talking here mostly about architecture and performance, which are easy to talk about. But if you look at Exascale plans, there's a very famous, by now, paper from about 2 years ago, which says the top 10 Exascale challenges. And 6 or 7 of those challenges have to do with exploiting parallelism, with fault tolerance and reliability, with system software, with scaling the system software. So it is well understood that all the other things are difficult, and exactly because of this move towards many core processors require significant new investment to really address those challenges. So, yes. I just want to put, sorry, did you have a question?
Yeah.
Yes.
I was curious what kind of studies have been done to relate the performance on LinPack to the actual real application.
I'm surprised that it took so long. Somebody asked that question. Thanks. Okay. Have studies been done? Well, since you asked the expert questions, you may be aware of some efforts in the last 2 years or so to come up with a different benchmark, which, to quote my friends there who work on this, to have a more realistic representation of the performance of a supercomputer. But I'm answering this question, I'm giving you a counter answer, and I say, what is what is more realistic? What's the real performance of a supercomputer? Can you express it actually in one single number? And I think that's the problem, is no matter what you do, if you restrict yourself to a single ranking of the system, you're bound to fail, or you're bound to produce something that's not really relevant, because a lot of applications have very different characteristics. So there's a subset of people who do some materials calculations which will lead to dense matrices. If you do that type of approach, you're very happy with a LinPack benchmark, because the majority of the calculations you're doing is factoring double precision complex matrices, and that's what LinPack just captures really well. If you do molecular dynamics calculations, the LinPack number doesn't tell you much at all about how molecular dynamics calculation functions. So I gave you a long answer. The answer is LINPACK is one parameter. The advantage of LINPACK is actually mostly its historical consistency, that unlike any other benchmarks, it has not been changed for 20 years. And so you can make comparisons of the type that I'm making here. I would say there are two reasons why LINPACK is also a good benchmark realistically. One is that it's like Hello World. If you don't have a working system, you cannot run LINPACK. So it distinguishes the non-working systems and the vaporware from working systems, which is actually, you may say, well, how could that be? But I can tell you more anecdotes where this was a real challenge for some initial systems to bring this up. One particular notorious example was so Apple was for a short time flirting with supercomputing and funded a group at Virginia Tech to build an Apple supercomputer. And that system made actually the number 3 spot on the top 500 list somewhere around 2003, 2004. And then they reconfigured the system. They could not produce LINPACK, so they were dropping off the list for 6 months until they got back on the list. So it is not easy for some special purpose built machines to actually do LINPACK. So it's the hello world. The other one is it is actually a very strong indicator of reliability, because currently to be on the top of the list, you have to run LINPACK for of the order of 6, 8, 10, 12 hours. And so that's a good reliability test for the high-end systems. If you have a new system, that may be harder than you think it is.
Is that new application HPGMG?
There are two. There's HPGMG is the multigrid is proposed, and then there is a conjugate gradient proposed. But these are proposed, and maybe I should say it this way. Actually, Top 500 does not have any official status at all. It's a hobbyist activity. I have to say, maybe this disclaimer, I've never received a single dollar of government funding to do Top 500. It's a condoned activity, and I think for a long period of time, our sponsors in DOE were not particularly favorable of Top 500, but after we had 4 machines from DOE in the top 10, then they were happy to see them in the machine. So it's always how things work. So sorry, Mike, you had another question.
Typically, we use LINPACK as the machine won't run faster than that.
That's true.
So typically, the LINPACK number is a good number in that is the best this machine's ever going to do.
Yep.
We don't use it for how well it'll actually run our apps. We just know this is the fastest it could ever run.
Yeah, that's hard. I mean, if you.
And it's a useful number for that.
It's a useful number. It's yeah.
Right?
It's like the way I compare this is what vendors say is the peak is just like you have a fast car and it says, the odometer says you can go 240 miles an hour. And what LINPACK is that you clean I-5, you go up Mount Shasta, you get a big swoop, run down Redding, and then you press the gas pedal until you hit Sacramento, and then you're at whatever, 150 miles an hour, and that's your LINPACK speed. Everything is clear, everything is taken away, just race. And just as Mike said, that's what it is.
So
You can't.
And then it's like embarrassingly parallel little synchronization?
No, it is.
It doesn't have a lot of communication.
It doesn't have a lot of communication. It takes advantage of matrix operations, so you can optimize quite a bit, especially if you have, say, GPUs or large caches. So anyway, but coming back to another interesting anecdote. So I had this conversation with my good friend and colleague Thomas Lippert, who is the director of the Jülich Supercomputing Center in Germany, and we were sitting at a really nice dinner in Switzerland in 2010, and we got into this heated debate, and I said, I bet you we won't have an exaflop system by 2020, and he said, we will have an exaflop system. And I said, well, let's be precise. Let's define that there will be a number 1 system on the top 500 list by November 2019, which has a LINPACK performance of greater than an exaflop. So that was our bet. And we agreed on this. And since this was 2010 or thereabouts, or 2011, we did some currency hedging as well, because I said I want €2,000, and he said he's happy for $2,000. And this was because Greece then, just like today, was sort of teetering along and doing, getting out of the euro, or anyway, there was some. So Thomas didn't believe the euro was doing very well, and we were sitting here and we had sequestration, and then of course we had we had a close down of the government, so I wasn't particularly convinced that $2,000 wouldn't. So right now, it's actually pretty even. So we'll see how this $2,000 thing versus 2,000 euro behaves. But actually, Thomas and I met last summer, and he was offering me, he was actually conceding. We said, well, we still have to wait until 2020, but he was offering me another bet. And he said, there will be no working quantum computer that is better than a system on the top 500 by 2025. And I said, don't bet with me. I'm completely with you, and you'll hear about this later. So I want to get my 2,000 euro. I gave a similar presentation in 2012. I said this. You can look this up. It's in HPC Wire and everywhere else. That at that time I was portrayed a little bit as an exaflop Grinch who took away rosy dreams. And I think today I'm pretty sure that I will win the bet, because the only thing which stands between us and an exaflop machine is a lot of money, $1 billion of investment, and maybe a power bill of 50 million to 100 million a year, because you have to pay a big electricity bill for this. So let me just briefly talk about the power efficiency. So just since I made this point here, what's the problem here with the electricity bill? So if you look at power efficiency over time, and so this is LINPACK power, and this is another thing where LINPACK is a good comparison. If you look at LINPACK power of the top 10 systems, that's the blue is the average of the top 10 systems. LINPACK divided by power of the machine. So it's gigaflops per kilowatt, or it could be also the same thing as if you scale up into petaflops per gigawatt would be the right scale. Anyway, so now it's petaflops per megawatt, because it's expressed 500,000 here. So anyway, the main point is that you got actually quite a bit more performance out of these systems as we progressed in time, and the power efficiency seemed to be better. And if you extrapolate this curve out to the future, it actually looks pretty good. This curve would tell you that an exaflop system you could get an exaflop system between 20 and 40 megawatts, more like 40 megawatts. So that's what this curve tells you. Now, 40 megawatts is still a huge amount of power. 40 megawatts, roughly speaking, is you can take this, depending on what, of course, your local electricity cost is, costs you about $40 million a year. So megawatt is $1 million a year in electricity bills that it costs you to run. So that would cost you, a 40 megawatt system would cost you $40 million a year to run. So it's still significant. Somebody brought up the big servers like Amazon Web Service and so on and so on. They have these electricity bills. So just as an aside, that's just for everybody who always thinks the cloud is free. The cloud costs a lot of electricity, and somebody pays for it somewhere. So it looks good, but the point I'm trying to make here is the following: is that this was a one-time technology improvement. That was the switch from basically to either GPUs or to many core. And the jump in 2010, you can pretty much say, was a jump when the first time a very large adaptation of GPUs happened. So basically, the two curves are actually on the same slope. That's again a claim, and we can debate this. And so we will, unless we have some other silver bullets like this architectural change to GPUs or to many core, we won't get on a good curve. So here it is, what I say, if you believe it has a continuous trend rate, we're going to get there, but if it's only a one-time technology improvement that got us from one curve to another curve, then it will be much more expensive, it will take much longer to get to the exaflop system. So therefore, I will say a little bit about beyond CMOS. And again, coming back to Miha's introductory question, where are the opportunities? I'll give you my comment on the beyond CMOS opportunities. So I will quote John Shelf, who was here before, and I think sometime in last fall, and my colleague Rob Leland at Sandia, who have a very nice, at this point, still unpublished manuscript called Computing Beyond of Moore's Law. It's a very great survey paper which has everything in there. And the interesting thing is that Shekhar Borkar and John Shelf, Shekhar is a scientist at Intel. I wasn't going to say chief scientist or chief technologist, something with that type of title. And they said there need to be 4 criteria for evaluating these post-CMOS architectures and alternatives. And it's very important. I think the scalable manufacturability is something that's very important because no matter what you come up with materials in the lab or in the university setting, you got to produce whatever you want to produce at a very high rate. And so there's a lot of technologies that are out there in terms of improving transistor performance, architecture advantage, 3D integration, and so on. They went through all these technologies, explained what they are, explained what the challenges are. And bottom line is, and I come to the bottom line, that there are two things which I think are A, promising, B, can be scaled, and C, have been already either adapted or announced by industry players. One is three-dimensional integration and packaging. So if you look at announcements that come by Intel for the Knights Landing type technology, they say they will have three-dimensional integration and packaging. And if you move further out, silicon photonics that is doing an integration of photonics even up and onto the chip, that's happening probably later. So both are moving into products now. So in summary, if you ask me, are there opportunities, I would say, yes, there are lots of intellectual opportunities coming up, but are there opportunities for the startup company to play a role? I think it's a big, big challenge because you have, what I said, the manufacturability, scalability, a long-term investment in hard technology that's very, very difficult to come by with. And the big players have already staked out what will happen in that space. So very simply put, I think we can reach the exascale target, but we'll reach the exascale target after two boosts. The first boost is this 3D integration, which will happen between 16 and 20. And the third boost is silicon photonics, which will happen sometime between 20 and 24. And those two boosts will get us on the right curve for getting power into a manageable, not small, but manageable range for building an exaflop computer. Therefore, if you want to build an exaflop computer before 2020, you just have to spend a lot of money and pay a big power bill. So that's my simple conclusion.
So what cost savings? Okay, so how much will the 1 exabyte computer cost after the third boost? I mean,
well,
significant difference in cost?
I would.
The same for the same money?
I think in the end they will cost what they cost today in today's money, of course, not predicting inflation. So the very high end, the very first systems say, to put a ballpark figure out there, $200 million. The Japanese spent much more on their first petaflop computer. They spent $1 billion. We don't know what the Chinese spent on their current number one on the list, but probably also more than this. The expectation is not to spend more. I should say the interesting thing is on both of these technologies is actually not enhancing floating point performance, but reducing communication cost, and in particular reducing, A, making communication faster, and B, making communication less power consuming. It's really the communication cost. When people say floating point are free, it's actually true. Floating point are free. Therefore, it doesn't make sense to build an exaflop computer. If floating point is free, why bother? What we really have to build is an, say, petabyte a second transfer computer. And that's where those technologies help. And 3D brings things closer together, so you have shortened the distance, and silicon photonics uses a new technology which makes bandwidth and faster. And latencies. So basically 2 boosts are needed, and the question is, you can look at the other technologies that are, say, in the shelf, Leland paper, and they may come to play after 2025. They will probably take a long lead time to actually get to a scale where they're manufacturability. I mean, if you look back, 3D was talked about probably 6, 7, 8 years ago, and it's coming 10, 12 years after it was first talked about. So if you're in for the long term, and if you get investors who are willing to fund you for 10 years, then look into any of the post-CMOS technologies and see how they can be turned into useful products. But you're up to a very long-term, long lead time there. Okay, I'm talking already a lot. I see I've spent 40 minutes, so I'm sure, well, let's rush. So here's quantum computers. There's no strict limit, but I want to limit myself. Well, 20 more minutes. We'll get this in 20 minutes. So quantum computers. So sorry, I may have skipped too quickly. I'm at number 3. So I gave you my beyond CMOS. There are lots of promising technologies out there. They take a lot of development time. Here's quantum computing. The folks at D-Wave who built one of the first, or the first commercially available quantum computer did a great job in terms of PR. They got themselves on the cover of Time magazine about a year ago. And I love the quote somewhere in the article. It says, and nobody knows how it actually works. I love a statement like this. If you don't really know how a computer works, it's a little bit dubious. And if you read this whole thing about the infinity machine and all the other things, it's clearly blown a bit out of proportion. And in particular, it's always good if you Google image search and you search for image of something you have no idea, and you search for quantum computer, you get this image. And that image tells you what the popular imagination is of a computer. It's again one of those mysterious objects that only exist in a lab with some lab-coded, white-coded scientist making strange experiments. You mentioned Tesla. It's back to Tesla coil, something strange here. Anyway, there is a mystique around quantum computers. That's absolutely clear. Now, I want to talk about a couple of things in quantum computing. I'm not, just to say this from the beginning, I think there are niche applications where quantum computers will make an impact, but I think we're still very early in the development of quantum computers, and there are a couple of big challenges. So the first challenge, which is very controversial is that if you ask people about quantum computing, everybody will tell you, well, there's Shor's algorithm, then there's Grover's algorithm, then say, and what else? And there's really almost nothing in terms of the algorithm world that has been developed in the last 20 years, even though the early promise was there, that would provably be faster than conventional algorithms. So where are all these quantum algorithms? Not out there. The other one is, even if there were lots of genuine new quantum algorithms out there, it's going to be really difficult, and this is true no matter what, to beat 60 years of classical algorithms research. If you go back and look at things that that many of you have spent their time on in terms of algorithms, say, let's take linear systems, where from the dense linear systems you went to sparse linear systems, you found multigrid. All these things, they took a long, long time to develop, and we haven't had this practical experience, and maybe it would go faster with real quantum computers and people actually spending more time on it. But at this point, traditional computing has a huge time advantage over quantum computing. So these two things are facts out there. So if we look about what's out there in quantum computing, there are really several approaches to quantum computing. I'll talk about the circuit model, the adiabatic quantum computing, quantum simulation very briefly. So the circuit model is something which is actually the most intuitive one to all of us who have been grown up with digital computing. This is that you basically build quantum algorithms or quantum computers similar to digital computers. And in particular, you want to use the same infrastructure that digital computers have. That is, the same design tools, the same verification tools, the same software. And that's basically as much leveraging what we know from the digital world into building quantum world. And this is pretty much that we build a box here called Oracle, and this is from my colleague John Kubiatowicz, Kubi at UC Berkeley, who went through all this. And the interesting conclusion that he has is that if you want to implement something like Shor's algorithm, the prototypical quantum algorithm with this circuit model, and you wanted to have, in a sense, error correction, and do this right, it would require about 500,000 qubits. That's huge, because if you follow very closely how many qubits have been built in quantum computers, well, D-Wave claims 512, but I'll come in the next slide, that D-Wave is not a circuit model, but it's an adiabatic, so it's a different type of quantum computer. So there's a huge gap in terms of getting there until we have the right infrastructure. It's in a sense, as I may have said this before, is in many of these technologies, we're at the first transistor. Maybe we have built 500 transistors in equivalent in the D-Wave machine. We're talking about 500 transistors and want to get to hundreds of thousands of 500 qubits. We want to go to 500,000 qubits. So this is just as much a jump as from Bell Labs in 1947 to, say, the first integrated circuits in Intel 4004 in the late 60s, early 70s. So big development time ahead of us. So adiabatic quantum computing is not general purpose computing. It's very special purpose computing. It looks at one particular system, the Ising model, and says find the ground state, the minimum energy state of that model, and does that with a particular mathematical technique, which is called adiabatic interpolation, which was pioneered by Eddie Farhi at MIT. And that requires some more mathematical explanation I'll skip over. And the point here is that there are a couple of things that are very much confused when people talk about quantum computers. Finding the ground state of an Ising model is an NP hard problem, and it's NP hard whether you run it on a quantum computer or on a digital computer. It's still a hard problem. The way the adiabatic algorithm behaves, irrespective of the underlying problem what you're solving, basically programming a D-wave machine means that you have to define in your problem the HJs and the JIJs and then put them on the machine. That's what it means to program the D-wave system. Finding them, programming them is hard because you don't really know what adiabatic schedule you have to get to actually find the minimum. There's a lot of debate whether D-wave actually exhibits quantum behavior. That's a separate topic. I would say it doesn't really matter whether it's a true quantum computer or not. You can look at this as a special purpose computer that solves a particular problem really fast. If it does it, great. But the question is it worth the cost? So the last direction I want to point out is what is called quantum simulation. And that's the work where quantum computers were originally defined by Feynman, of course. And he proposed originally about in the early 80s the first quantum computer. That's saying use a simpler quantum system that you can control to simulate the behavior of a complex quantum system, therefore make conclusions about the complex quantum system. So in a sense, it's an analog, if you want to use the term quantum system type computer. And I think that's a good approach because if you look at what's done on digital computers, a very large amount of cycles, at least in the science case, is being spent on simulating basically Schrödinger's equation. So if you can build a simpler computer, if it's just a Schrödinger equation simulation computer that solves that, would help a lot in chemistry and material science. That might be actually realizable before general purpose quantum computing because some estimates are that you can actually get by with a much smaller number of qubits and can get some interesting physically meaningful simulations done on those smaller number of qubits. But it's all work in progress. So I'm skipping over this, and I want to get to neuromorphic because I put it last because I believe that neuromorphic is actually the opportunity for folks like you who are looking for opportunities, and I will save this hopefully in a few slides. So if there's everything else, if you forget everything else in this talk, this is probably the one slide that you shouldn't forget because it is the most intriguing slide of them all. And this is what I would call the power conundrum of the human brain. I didn't go through the detailed analysis, but there is a way of making a case that once we have about a 1 to 10 exaflop computer with about 4 petabytes of memory, that computer would be powerful enough to simulate the circuitry of a human brain in real time. So why that is we can discuss offline, but let's just assume that this is a true statement, and there is actually a paper that my colleagues at IBM and I have written about 2 years ago, 3 years ago, which makes that case. But let's take what I said before, that such a computer, the first, say, 1 to 10 exaflop computer, would cost between 20 and would take between 20 and 30 megawatts. Then you have basically a 10 exaflop computer taking 20 megawatts to do about the same thing what the human brain does in 20 watts. And so you have a factor of 1,000,000 in power efficiency of the human brain. To say this one more time, the brain is 1,000,000 times more power efficient than current digital technology trying to simulate a brain. And so if you have a factor like 1,000,000, you say, what are we missing here? And actually, it's very clear what we're missing here, and this is becoming clear on some yes, Timo.
What exactly would we simulate?
Pardon? Well, very good question. That is just basically assuming that you take not actually thought or any action, but just taking the wave of connectivities in the brain, that is for neurons and synapses, model that in a statistical sense, that you have the right number of neurons, the right number of synapses, the right connections, and then model that you have every 20 or 30 milliseconds, basically that as a clock time to have the electric impulses going through this network, triggering more impulses, so that you can write a simulator which does that. So this is basically nothing more than a complex set of ordinary differential equations which model that electric propagation. There's no assumption, no statement made here at all that and I actually want to be very clear about this, I don't claim at all that an exaflop computer would have brain power in terms of the cognitive abilities of the human brain. I'm just saying that just in terms of electric circuitry, that's what the brain operates at, and that's what we would have to build with a current technology digital computer to mimic the brain circuitry. So the reason why that is, and there's a very important paper on this that appeared on August 8 in Science just 5 months ago. And what the paper argues is very simple, is that if we look over time from, again, 2004 to the latest digital processors, we've increased the clock frequency and we increased the power density. Of course, we hit the limit on the upper right is because now we can't increase the power density anymore because we hit basically the heat limit. But if you look at where the brain is, it's exactly in the opposite direction. The brain is down here. It's where it has a very low frequency. As I said, it has of the order 10, 20 millisecond frequency, and it has a very low power density. As I said, it's 1,000,000 times less dense than, say, the high-end supercomputers. And so, in a sense, our technology has driven us further and further away from a brain-like computer setting than where we would want to go. So the interesting thing is, in the last 4 or 5 years, there has been a lot of effort being put into neuromorphic projects. There are a couple of them listed here. In particular, what's interesting is that both IBM Almaden and Qualcomm, that is commercial companies, have invested in this. The European Human Brain Project has invested a lot of money into projects.
Which one is this one?
So the Spinnaker and Brainscales are a Human Brain Project.
Right. That's the one done in Switzerland.
One is in Switzerland, well, one is in Heidelberg, and the other one, the overall Human Brain Project is run out of Switzerland. The actual technology is done in Heidelberg and in the UK. So this is just up there to show you that I think any technology like this, it's actually good to see many approaches in different countries and both commercial and universities going after it, because it gives you an indication that this technology is right and this technology is ripe. So very briefly, this is IBM Almaden and Dharmendra Moda. These are some of the characteristics of the Synapse project. The chip that they built, the True North chip, has as the characteristics here is a 5.4 billion transistor chip. It's done actually Samsung technology. So it's very traditional technology. I think it's, 27 nanometers. So it's nothing fancy in terms of the actual technology. So it's digital, traditional CMOS technology, but implementing a very different architecture. And it has an incredible low power consumption. When compared to a simulator, it's built with the ability to scale to very large systems. So you have a board here, and those can be stacked together. So that's something that might be explored. And there's a programming model. So think of this as a, if you want to be very naively expressing this as a neural net or hidden Markov model or deep learning algorithm, take any of those connectionist algorithms implemented on in hardware. The important thing is, and I just show this as an application, that's one of the DARPA benchmarks. So DARPA invested in this particular project 50 million, invested in a couple more projects. Significant amount of money is to basically run this scene detection algorithm and distinguish between pedestrians, bicyclists, and cars. And there's a simple test that's one of those DARPA challenges. And the important thing is that you can run this test, and it takes on this very simple challenge significant. Let me say it the other way around. If you run it with this neuromorphic chip that IBM did, you can do this basically in real time, and you cannot do it in real time. You can solve the same problem, but you have to run the simulation much slower. So they've proven, as far as DARPA is concerned, their case. And what they have done is basically, and that's why DARPA is interested in, this is technology they want to have low power, because you could put this into whatever, a tank or an airplane for target detection. You could even think of this in a heads-up display for a Marine or for an infantryman, so that they could scan a much larger field of vision and see what's moving. So that's clearly why DARPA is interested in it. But what's actually really important about this is the following, is that this thing is, well, I should go back here. This thing here is really small. I mean, it's a simple chip. And the simple chip has the equivalent of about 4,000 cores, 1 million spiking neurons. So it's a significant piece of the brain. I mean, the brain has about 100 billion neurons, so you still have to build a much larger system if you want to hold the whole brain. But what you can do with such a single chip is the following. You have basically, the way I would say it is, developed, if our traditional computers are floating point computers, going back to where I started, that support computational physics tasks like modeling the climate or modeling nuclear weapons, this is an element that you can use to do cognitive tasks, that is pattern recognition. And we all know that the human brain is just superb at pattern recognition. So that's maybe a technology that you can take and build pattern recognition systems. So one direction would be, of course, to scale this up and integrate this into HPC. But I think the much more exciting technology is that you should think about, if that technology were available, if you could get a pattern recognition chip and put it in any digital device, say on your cell phone, you could come up with hundreds and thousands of exciting new applications. And I can just tell you one that's actually not my idea, but that's the one. So I met a number of colleagues here, like Dave Stewart, whom I didn't recognize, but if I had this little thing in the iPhone, I would take a photo of him and do instantly a natural aging and look it up in my LinkedIn database and say, this is Dave, and you met him 2 years ago at the energy efficient computing meeting at the Silicon Valley Leadership Group, and that whispered in my ear through my Bluetooth earphone device, that I would be a very perfect conversation and say, oh, good to see you, what have you been doing in between? So that's just one application. So you can easily think about something like this. If you had this technology in this low power integrated way, and of course would have the way of programming it. And so while I am an HPC guy and say we should scale this up and have big brain models and try to do measurements and compare what the brain is doing, you could also simply say, doesn't matter if it's brain inspired or not. It's just a different architecture that does pattern recognition quickly and easily. So the way I put it is that the opportunity here is, if you think Raspberry Pi for brain computing. And that's, I hope I said this somewhere here. I thought I said, pardon? I said it on the previous slide. Anyway, yeah. So I think that's what for you the real group is. Now, this is probably 2-3 years away. I don't know whether IBM is going to release the chip to the general public, what they actually do with it. As I said, it's the end of a DARPA project. DARPA is happy with the success, but if DARPA is happy with the success, we probably have some follow-on projects where they will say, well, test it in some rugged environment, do some commercialization of this or whatever else, so we don't know this. But you should be just generally aware that this technology is out there. I mentioned Qualcomm is doing this. Qualcomm is doing it for exactly the set of applications that I've been talking about, the low power pattern recognition for mobile devices. So in summary, and I want to wrap this up because I promised to be done in an hour, and I think it's almost there. Slowdown of Moore's law. I think that that will create a change in the HPC world. Not clear what it will do. Unpredictable dynamics. As I said, some big players have gone out of the high-end computing. IBM has given up one line. Who knows what's going to happen? I think the current trend in terms of investments is very good. We have the Exascale program, at least in the federal government, going forward. The EU is very strongly behind computing, so is China. So I think those technology investments and the overall investments will get us to Exascale in the early 2020s, maybe by 2025. By that I mean that we get 1,000 times the application performance of today. I think quantum computing should be pursued as an intellectual pursuit in the academic environment. I think it's way too early to think about this in commercial environment. I mean, I can be proven wrong. You can invite me back in 10 years, and if I'm still interested, then we'll see what happened. But I think that on the HPC side, we'll evolve towards a hybrid model, integrating new architectural concepts. Neuromorphic is one that's currently there. Others could be out there that do other things. But I think the huge potential, as I said several times now, is in looking at what something like a pattern recognition engine could do in mobile devices. And so with that, I'll end and be happy to entertain any questions.
Questions? Yeah, please.
I have two questions. One is what kind of technology that right now using this neuromorphic computing that's bringing down the energy consumption and improve the energy efficiency? This is the first question. The second question is that do you think that this neuromorphic computation can be the general purpose computing? Because probably it's good for the pattern recognition, but for like some application using the linear algebra,
Yeah.
probably it's not so good.
So I think it's going to be probably a stretch for the second one in terms of will it be a general purpose machine? I don't know. I don't think so. It's just like, as I made the point before, our supercomputers are doing really, really well in multiplying floating point numbers together and have exceeded the brain capacity in this. And it's kind of miraculous that the same high floating point performing computers can also do all the other things that we like to do, such as social networking and web searches. So yes, it could be done with lots of development, but I would say not in the near term. The other question, if I understood this right, was basically, if I go backward, well, I'm just going to go to one specific slide, which I think is the key slide here. Oops, this one here is, so the brain chip that IBM has, and the reason it reaches that performance is actually not clocked very high, but also avoids a lot of communication. So it is actually, if you want to say it this way, almost like, I don't know what the real word is. I mean, they say neuromorphic or brain-like. It is that the individual unit that you have for computing here, the synaptic core is exactly doing what a synapse is. So it's a simple thresholding. It collects inputs and then produces an output. So what you have is you have memory and computing integrated, and you have many nearest neighbor connections, so you don't have long distance communication, and you're using a very low-powered, low-end technology. So I think it's, if you try to analyze this, I think it's mostly the fact that you don't do much computations of the traditional kind, and that you do, okay, you gotta fix this somehow.
Yep.
Which I don't know.
Let's do this. We'll come back there.
Yeah, I should go here so that we get this right. There we go. Okay, so I think I answered your question. Okay.
More questions?
Yeah, I was just kind of curious. I went to a Flash summit last summer
Mm-hmm.
with a discussion of all the upcoming non-volatile memories. that are
Right.
coming out, resistive RAM, magnetic RAM, and all this. And with a discussion that they may eventually get to be as fast as DRAM.
Yes.
So I saw some article discussing this, reminding that a lot of the architecture, the design was in the assumption that volatile memory was going to be many, many orders of magnitude faster than your persistent storage.
Mm-hmm.
But if that's not necessarily true in the future, I was kind of wondering how the architectural changes might influence, well, any of these computing systems.
That's a really good question. I haven't thought this through. So some of you know that we signed a deal with Cray and Intel for a fairly large-scale system in Berkeley that has a lot of the flash technology in there, exactly for doing some more data analytics. And so certainly the availability of that type of memory will change what can be done on the very high end in terms of data analytics. But if you push it one step further, how it would change overall architectures.
Well, I mean, the flash is still slow, but when
Yes.
there's a lot of promise apparently
Yes,
in like
yes.
resistive RAM and
Yeah.
NRAM of actually getting to the point where it's about as fast
Yeah.
as DRAM. So then, how do you design your architecture now to take that into account when everything is
Yes.
persistent, and how would that affect, your design?
So I would say I don't know the answer to that, and you might want to ask one of my colleagues in 2 years after we have had more experience with such a system and what we're doing with it. It actually has become, so actually Intel and Cray have actually invested some research dollars at UC Berkeley to look at exactly that type of question. So, sorry. It's a good question, but no, I don't know the answer. And
It may be a little more disruptive a technology
Possibly.
than a lot of people really think of. Right now, they just think of storage, replacing.
Yes,
the
yes,
capable
yes.
drive
You're right. You're
with
right.
But this seems like it may go well
Yeah.
beyond that and change
Yeah,
a lot.
actually, I haven't heard anybody asking the question the way you asked it, but it makes me really think that we should construct the answer to that. Thank you.
I think the first person over there.
Sure. So what's your personal favorite for the programming model that's going to be the easiest to work with at Exascale? Or do you not-
Well, I don't have a personal favorite, but I can tell you that what I believe is going to be a MPI plus OpenMP. Yes.
Yeah, UPC.
Yeah, I'm coming from Berkeley, and so I should say UPC or PGAS, but the reason why I say this is because I look at what people are currently doing, and that's exactly what they're doing. And so there might be some variant on this, but you asked me. It's not my favorite, but I think that's what's happening.
You can just stick with the same.
It's sticking with the same. It's just that the Exascale system will in all likelihood be a system which has some very large, powerful CPU and attached or maybe integrated, but still it will be, in a sense, a hybrid processor with one large CPU certainly and a many core attached to it or integrated in it. And so if you look at this, then you do an MPI. If you think that this is the model, then you will do MPI on the CPU and do OpenMP or some such thing on the attached, or maybe not so attached. I shouldn't use the term attached, but
Yeah, the accelerator.
accelerator.
So you think it's going to be more Intel Xeon Phi, not host plus CUDA GPU, right?
Yes, I think so. And I would actually expect that NVIDIA will develop things that are more tightly integrated in the near future. I mean, it's inevitable because everybody says it. I mean,
They already announced that in Gorham, right?
they've announced it. Yeah. Okay. Good. I have to. I was hedging my words.
Would NVIDIA be used for neuromorphics as well?
No,
Or is it different?
it's too heavyweight. I mean, there wouldn't be even the support on this type. The individual neurosynaptic core couldn't support anything fancier.
So the slide that had the 4 different things, CMOS, beyond CMOS, quantum, and neuromorphic, those are all looking at processors, not
Yes.
communications.
Yes.
And communications is where the breakthrough is needed.
Yes.
So do you have anything to say about new technologies in that area? We've got power, et cetera. I mean, obviously, we've got silicon photonics, as I mentioned, but
Yeah, that's what I was going to say. I said I wasn't completely ignoring this, but if you go back to what I actually said was here at the end of this, that if you look at all these things, several of these are also relevant for communications, but then if you look at the things that I believe are actually happening, all are applying to communications more than to computation. There's the new technologies, if you think about it, is integration just shortens the distance and brings memory closer by, and silicon photonics reduces latency further. And so these are communication tools, but I think what you're waiting for is something which is much more an integrated way of integrating communication and processing, and think about this differently. So I think that's the next step. So neuromorphic is one of those. But that's I think why I say neuromorphic is just one of the examples. I think we have reached a point where actually architectural experimentation is again very, very important, and hopefully there would be 50 different university projects that pursue things like that. And then maybe one or two will survive and do something commercially viable. Yes? Sorry.
I have a question later after this. Is it possible to communicate with you?
Yes, yes. I mean, I can give you my email, or it may have been on the. Well, yeah. I'll
Any other questions?
I have a vanity question. So since '94, the top 500 list of competition power. At what point or have we already crossed that point? That something in my hand that I carry in my pocket sort of reached that list at number 500?
It's unlikely because they're always bigger machines. It's one of those.
I'm sorry. I'm saying like the 1996 model.
Oh, yeah, that has happened a long time ago. So what you held in your hands would have made the top 500 list 20 years ago.
20 years ago?
I mean, probably even later than that.
Fairly correct.
It's an amusing anecdote. It's not exactly a top 500 anecdote, but I think it gives you a sense on this. I was at NASA, and I had a summer student from Stanford, and I know this was in 1988 probably. And I gave the summer student a certain problem to solve, which he spent, computational problem to program it and find the solution, and do this on a Cray 2, which was one of the most powerful supercomputers of the time. He spent all summer long and he didn't finish it. Then I was sitting in the car picking up a visitor who was at Stanford and bringing him to Berkeley, and we were driving by where Sun was, and now, at that time Sun was there where now Facebook is. And I picked him up at Stanford, and somehow we came to this project, and I explained this to him, and I said, I bet you I can solve the same problem with MATLAB on my laptop. And so this was so it was 88, that was probably 2002 or 2003. And I said, well, let's see how, and I said, yeah, I believe that. And then he pulled out his laptop, he started it on MATLAB, he started it running, and we were done before we crossed the Dumbarton Bridge. And so you'd say, well, you have the processing power. I mean, this was whatever, 2 gigahertz laptop, so it was a good laptop. But we figured out that probably because he was running on battery, it wasn't running at full speed and other things. But in short, you get the picture. And so I can't give you the exact point, but yes.
Any other questions? If not, let's thank Horst again.
So